Hello, everybody. We'll be talking about the GHOST system today. This is on the paper on the value of oversampling for deep learning and software defect prediction, published at TSE last year. I'm Rahul Yadida. I'm a PhD student at NC State, and I co-authored this paper with Dr. Tim Menzies. We'll be discussing this in the context of software defect prediction, where you have, in our case, static code features about different files of source code, and we want to predict if there is buggy or not. Now, because of the inherent nature of this, these defect prediction datasets have a class imbalance issue. Consider the 10 datasets shown on the left. These are from the promise repository, and they have class imbalance in the training sample. Remember, we're only fitting on the training set. So in many cases, such as IV and Xerxes, there's a high class imbalance issue, and in other cases, such as Lucene, there isn't, and that's fine. But when you have class imbalance like this, consider you get decision boundaries that look kind of like the one shown on the right. It's not perfect. I would say this is overfitting a little bit as well. And this is pretty typical. In fact, sometimes you'll also get cases where the learners, such as deep learners, tend to predict everything as the majority class. And so that's the problem with defect prediction datasets. And how do we solve this? Well, the trivial solution to this is to do something called oversampling, where you just go to the minority samples and add more points right there with the same class. There's a better way of doing this. You can do what's called a weighted loss function, which is what we did. And so consider a loss function, which is what the deep learner optimizes. And we've broken down that into two parts, the one for majority classes and the one for minority classes, say C0 is the minority class. For the minority class, we've added a 1 over n fraction, where n is the fraction of samples with class in that minority class. And we've added a weight factor wi. It turns out the actual weight itself doesn't matter, but what matters is that you have 1 over n. And it doesn't, and although you would think that the oversampling would help, it doesn't. We've got the decision boundary in our toy dataset here, as shown here. It's still pretty bad. It's predicting most of the majority of the space as the blue samples, which are the majority class. And you see that in our actual datasets, this doesn't do well as well. So these are median F1 scores, and we're also showing the interquartile range, the IQR, which is the difference between the 75 percentile and the 25 percentile. And you'll also see that we're not doing well. In fact, the IQR has gone down, so it's slightly worse than if we hadn't oversampled at all. So how do we fix this? Maybe we use better oversampling techniques. We don't just do random oversampling. We don't just do weighted loss functions. We use something like SMOTE, which adds points between two minority samples of the same class. And so we can also take hints from literature. There are several papers suggesting that hyperparameter optimization is a good thing. And we're using the Dodge algorithm because there are papers by Agarwal et al., please read their papers, which say that Dodge works better than something like HyperOpt for SE datasets. There are others, better ways of doing this. See the paper by Rui Xu et al. In 2022, where they use Wasserstein GANs to resample the dataset, but we won't be exploring that here. We'll just be using SMOTE. So does using SMOTE and hyperparameter optimization work? And no, it doesn't. It's slightly better. We have a higher IQR, which means we are trending towards the right direction, but we're still getting a bad performance fundamentally. And so at this point, we have to reflect on why this is the case. And the insight here is that the decision boundary is too close to the data samples, which means that if you have a test sample that's actually close to the training sample, it might fall on the other side of the decision boundary, even though it's the same class, actually. And so we want to push this decision boundary away. And one way to do that is to add points around these minority samples. And we call that fuzzy sampling. And that's what we're showing in this code segment. Look at the first for loop, the topmost for loop, that goes over all the samples in the minority class. The next for loop goes concentrically around these points in a certain range, in increments of certain radii. And the final for loop decides the number of points we add there. So we have an exponential decay, that's the power 2 comma I you see in the denominator. And we're using the 1 over for n, which is the 1 over frac that you see here from the weighted loss function. For a full demo of fuzzy sampling, please see the link on the left. So does fuzzy sampling work? Yes, it does. So number 5, 6, 7 all use fuzzy sampling. What's common between them is they use fuzzy sampling and hyperparameter optimization. So it seems like this is a good combination, even though the performance seems to be the same across all of them. What's also common is that they're using some form of oversampling. They're either using SMOTE or or weighted loss functions or both. Now we need the oversampling additionally because although fuzzy sampling is an oversampling technique, it reverses the class imbalance. It doesn't actually balance the classes. And so we use an oversampling technique to make it better, make the classes balanced again. And so this is showing some promise. This is our solution 0.8, so we're nearly there. What we can do better still, and how is that? We can also do the same for the majority samples. We can do fuzzy sampling for the majority samples and say maybe there are data samples in this test set where the test sample is too close to the majority class sample in the training set and the decision boundary is cutting it off and misclassifying it. So now we do fuzzy sampling twice. We do fuzzy sampling for the minority sample set. We do fuzzy sampling for the majority set. This causes a class imbalance, so we use SMOTE and oversample and weighted loss function to cure that. And we use hyperparameter optimization to find a good configuration for the deep learner. This yields our excellent results, which are a median F1 score of 80%, and a healthy IQR. This system we're calling GOES, and it yields the state-of-the-art results for defect prediction. In summary, we oversample on the minority samples using fuzzy sampling. We oversample again on the majority samples using fuzzy sampling. We oversample a third time using SMOTE to fix the class imbalance caused by fuzzy sampling, and we also use weighted loss functions. By the way, fuzzy sampling also improves the beta smoothness of the loss function, which means it's easier to optimize over, but that's for a different upcoming paper. Thank you for your attention. If you want, you can read our paper at the link here. You can also see our fuzzy sampling demo at the link. These slides are also available online, and you can contact me at this email address. Have a good day.